Hello and welcome back to Math Class in Session. Yet more optimization problems. Couple more for you here today. Consider a sphere. We want to find the maximum volume of a cone inscribed into that sphere. Take a look. There's the cone, there's the sphere. And we want to maximize the volume of this cone, which is inscribed inside the sphere, of radius 7 centimeters. The sphere has radius 7. Solution. Well, first, the sphere has properties, and one of those properties is it has a center. That's a useful point. Let's put it. Now, from that center, there's a radius that goes to the edge. Now, what we learn to do is draw useful radii in a sphere. Useful radii. That's a useful radii because it's part of the height of the cone. So we know that that's 7 centimeters. That's going to be a useful radii because it goes to the edge of the cone. So we know that radius is 7 centimeters. And now we can fill in the height of the cone and the radius of the cone. So we have a height of a cone and a radius of a cone in front of us here. We don't know what that is. So there's a missing piece here. We can call it x. Now we know the height of the cone is 7 plus x. And Mr. Pythagoras steps forward to give us the radius of the cone, the square root of 49 minus x squared. Now, cones have a formula for their volume, pi r squared h over 3. Pi r squared h over 3. And for this particular one, h is x plus 7, and the radius is root 49 minus x squared. Plugging them into the volume of a general cone could look like this, pi r squared h, where r is the square root of 49 minus x squared, and h is x plus 7. And with that done, the hard part is over. And now it's time to prime it, zero it, and solve it. Squaring out the square root. And I'm going to take for granted that since this is grade 12, multiplying and collecting like terms right in here is easily done. I took out the negative sign and I extracted the 3 from underneath. And so we have this factor in front and we have a cubic inside these brackets when you multiply out these two binomials. Take a piece of paper and confirm that this is true. I'm more comfortable with positive reading terms in cubics. That's why I pulled out this negative sign right here. It's a matter of personal taste. Differentiating comes next because we're supposed to prime it. So differentiating, we know that the derivative will be the negative pi over 3 factor times the derivative of the polynomial, which is going to be 3x squared plus 14x minus 49 like this. And setting this derivative equal to 0 leads to just the resulting quadratic equated to 0. We can drop the negative pi over 3 factor because if a product of factors is 0, one of those factors being 0 will be sufficient. So we know that pi over 3 is never 0, so that's our rationale for dropping it. And solving a quadratic equation. Factoring is good. And this leads to x is either negative 7 or positive 7/3. Well, obviously from the diagram, x is not negative 7, so x is 7 over 3. And the volume for 7 over 3 is 425.7 cubic centimeters. Please don't take my word for it. Take 7 over 3, plug it into the volume expression. This one here looks inviting, possibly even this one here. Plug it in, do the math, and confirm that yes, the volume is 425.7 cubic centimeters. An interesting observation might be, I wonder what percentage of that sphere is taken up by that cone. It's just a question that naturally arises. Well, let's investigate. The volume of the sphere is 4/3 pi r cubed. And if we sub in an R value of 7 into that formula, we get 1436.8 cubic centimeters. And performing the division, the volume of the cone divided by the volume of the sphere, 425.7 divided by 1436.8, and we have 0.296. And we can conclude that the volume of the cone inscribed inside the sphere takes up 29.6% of the volume. Let's do another example. Find the length of the shortest ladder that can reach a building to be painted if it has to lean against a walkway that is 2 meters wide and 3 meters high as shown. And we can see this woman walking underneath this protective walkway over the sidewalk, which is 2 meters wide, and this walkway is 3 meters high. And here's the painter on his ladder, and we want this ladder to be a minimum length. What's the shortest ladder? Well, the solution can go like this. Observe the diagram and draw a perspective of it like this from one end. This is like walking down the sidewalk, and we can see that the width of the walkway is this 2, and the height of this walkway is this 3. Now we're going to pull the ladder out here a certain amount to make room for some room so that the ladder can lean, pretty obviously. We don't know what amount. We can call that X. And this ladder will reach to some point on this wall up here, which is above the walkway, and we don't know how high that is. So we're going to have to give it a name. How about Y? And we can use Mr. Pythagoras to tell us that this distance along this small triangle in the bottom corner is the square root of 3 squared plus x squared, or x squared plus 9. And the other part of the ladder here is going to be the square root of y squared plus 2 squared, or y squared plus 4. And so the length we're trying to minimize is the sum of these two square roots. Now, the whole idea of trigonometry is based on similar triangles. We can see that the triangle on the top, this one that I'm outlining, is similar to the triangle on the bottom, which is this one that I'm outlining. They're similar because they have the same angle. Now I can demonstrate that they have the same angles, and those are the angles that I'm going to demonstrate are true, because there's an F pattern here between parallel lines. The roof of this structure is parallel to the ground, and so this line is parallel to this line, and therefore the angle in the corner here must be the same as the angle in the corner here. They're called corresponding angles, and they form, in this case, an upside down and backwards F pattern. So we have a couple of equal angles, and in those two triangles, they're both right angle triangles. That makes two angles the same, and both of those triangles must therefore share a third angle. All the angles in these two triangles are the same, the one on the top and the one on the bottom. Therefore, the sides must be in proportion. So y over 2 must equal 3 over x, which is going to be useful to us. Y over 2 equals 3 over x. And this, of course, implies that y is equal to 6 over x. This is useful to us because when we express our length, the length being the sum of these two square roots, we can replace y with 6 over x, and of course when you square it, you get 36 over x squared. And now we have a length in just one variable. And now we have to do our trick, which is prime it, zero it, and solve it. This. And it's an algebraic exercise, and it's worth following. Because certainly if you can do this, you can do any one for grade 12. So let's prime this, zero it, and solve it. Carrying it forward, there it is. Let's get it ready for priming. I perform the operation of addition of fractions underneath this root sign. Now it's strategy, you have to apply techniques. The technique I'm applying is adding fractions. This is 4 over 1, so when you perform the operation of addition, you get 36 plus 4x squared over x squared. Doing some more algebra, I factored out a 4 here, with the strategy and the intent to drag this 4 outside this root sign and make it a 2. I also took the square root of the top over the square root of the bottom, and the square root of the bottom is just x. Now I'm up to here, and I'm going to take this 4 out. It will be a 2. So we have, this is a little easier to differentiate, in my opinion. We could start right away by differentiating this, but it just seems easier to process it a bit. Add the fractions, take root of top and bottom. That takes the square root off the x. And so take the 4 out, we have 2 here. And you can see that it's maybe getting ready a little bit to differentiate. Turn those root signs into brackets with exponents on them. X squared plus 9 to the 1/2 is the same as the square root of x squared plus 9. And now it's time to differentiate. Ready to differentiate, and away we go. I would recommend that you have a pencil and a paper with you while you watch this video. Pause it and follow this algebra. Make sure you agree with every step. Make sure that you can do it too, because you can. Okay, now differentiating. We'll do it term by term. So it will be top thing prime times the bottom thing over the bottom thing prime times the top thing divided by the bottom thing squared, because this is a quotient of functions of x. So top thing prime will be half times 2, and that's just 1, times all of this to the minus 1/2, times the derivative in here, which is 2x, times the bottom thing. So what we have here is top thing prime times the bottom thing. Dwell on it until you agree. Minus the bottom thing prime. Now we're differentiating this, so it'll be the bottom function primed, which is just a 1. So it'll be subtract 1 times this top thing, which is what I've done here. Minus 2 times x squared plus 9 to the 1/2. So this is top thing prime times the bottom thing minus the bottom thing prime times the top thing over the bottom thing squared. Squaring x, we have that. So this term is differentiated. Let's do this one. This one's easy to do. It's 1/2 times all of this to the minus 1/2 times the derivative in there, which is 2x. And there it is, differentiated. So we're supposed to prime it, zero it, and solve it. Well, there it is primed. Now we have to zero it and solve it. Well, first let's tidy it up a bit. Let's see what we can do here. Tidying it up. Well, that's quite a leap. What did I do? There's 2 terms. What did I do to this first term? Well, first of all, I multiplied top and bottom by x squared plus 9 to the 1/2. So you can see that x squared got multiplied by x squared plus 9 to the 1/2. Why did I do that? Because when I multiply this times x squared plus 9 to the 1/2, this becomes x squared plus 9 to the 0. That's just a 1 times. So we can drop it, and that just leaves 2x squared. And when we take this and multiply it by x squared plus 9 to the 1/2, we get x squared plus 9 to the 1. So that's why it says minus 2 times x squared plus 9. And it's tidying up. I certainly consider this tidier than this. And over on this term, it's a different term separated by a plus sign. 2 times 1/2 vaporizes. X remains in the numerator. That's why it's in the numerator here. And this factor, x squared plus 9 to the negative 1/2, turns up in the denominator. Now, what can we? I've also set it equal to 0. And our task is to solve this equation for x. Here we are, solving equations. Grade 12 math. Yes, master this, and you can take on any university course. Performing the operation of addition of fractions. That's going to help me to solve this equation. Here we go. Well, the common denominator will be this denominator, because this one is a multiple of this one. It's x squared times it. So I can just copy in this top. And this one right here will be, well, what did I multiply this factor by to turn it into this denominator? X squared. So I have to multiply x squared times x, which gives me this positive x cubed here, because we're adding. That's where this x cubed came. And when you simplify this, because we didn't change the denominator, 2x squared minus 2x squared turns into vapor, and we're left with negative 18 or minus 18. And performing an addition of fractions has tidied it up considerably. And it's equal to 0, so the numerator's got to be equal to 0. Set the numerator equal to 0, solve it, and take the third root both sides, and we have x equals 2.62. And finally, answering the question, what is that shortest ladder? Well, let's go back to, therefore, the shortest ladder is its length. There's our length of our ladder. It's the sum of those two original square roots, and plugging in 2.62 for x, doing the math, and we get the shortest ladder, 7.023 meters.